Hello, in this episode, we'll overview neural networks and introduce artificial neural networks. So what are artificial neurons? Well, in the 1950s, two scientists, Hodgkin and Huxley, observed in a giant squid how the neurons work and figured out the mechanism of biological mechanism or chemical mechanism of how electric signals are transmitted in a neuron. And that excited them a lot. And basically the idea or the summary of the findings is that, there's a part that's called dendrite, which is a receiving center, which receives electric signal either from outside or from another neuron on multiple inputs. And when the input is larger than certain threshold, then it shoots down an electric signal to a longer branch, which is called axon, and then it transmits it to another neuron or an output. Okay. And the interesting part was that, well, the multiple input, as you get more input or stronger input, it's not like it's if you get 1 unit of input, you transmit 1 signal, electric signal, and 2 units of input, then 2 units of electric signal. Not like that, but rather it's a threshold activation in that when the input is small, then there's 0 electric signal transmitted. And when it exceeds a certain amount, the sum of it exceeds a certain amount, then just 1 unit of input is transmitted. So it's like an on-off switch rather than a continuous gradually strengthening electric signal. And since then, scientists, neuroscientists, and computer scientists were excited and tried to implement it because the nature, like the animals or birds fly and all this, the nature solves a lot of problems with their neurons. So they tried to mimic this in a computer algorithm. And here, for example, Rosenblatt in the late 50s came up with the idea of Perceptron, which is like an elementary neural network. Basically, it takes multiple inputs like weight input A and input B with some weights, and then they sum it. And when the sum is larger than, let's say, 1, then it will transmit a signal. And this activation function we call can be just literally just exceed a threshold and just do this, or can be an S shape, but here it rapidly increases to unit 1, but it's a little bit smooth. And with that perceptron, scientists try to implement it in daily binary decisions. You may recognize it as a Boolean algebra. For example, if I did my daily exercises and I finished my homework, then I can have a cheesecake. Or if I get 1600 on the SAT or I get 36 on the ACT, then I will be happy. So like the Boolean logic here is that, well, there are 2 inputs, nothing or only B or only A or both A and B comes out. The A logic will get only positive signal if both are yes, and the OR signal will give a positive signal if any of them are positive. So how you implement this is that in this is that, well, these are input A and input B. So if nothing or only one of them lighted, then nothing happens. But if both of them are lighted, then it's transmitting a positive signal. In this picture, like above this dotted line, it's a positive signal. And in a perceptron, basically how you did it is that, well, you have the input signal 0 or 1 and output signal 0 or 1. If you have a weight of 0.5, only if both are 1, then it gives a positive signal. Likewise, on OR circuit is that if any of the A or B are positive, then the light is on, but it gives a yes signal. And that's implemented in a perceptron as having a weight of 1 in both inputs. So if either of A or B are 1, then the threshold will pass 1 and then it will light on. So they were pretty excited, and there are many things that could do, which led to the excitement in the 50s and 60s about the AI boom. Why don't we have perceptron these days? Or rather, the question is, why do you have not neural algorithm, rather we have a neural network? Why do we need multiple layers of neurons? And that started with some fairly simple question that was posed by MIT professors Marvin Minsky and Peppard in the late 60s. It's called XOR puzzle. And here again, our input A and input B, 0, 0, 0, 1, 1, 0, 1, 1. Okay? And the way it looks like XOR is that it is not on OR. So only if one of them is a positive signal, then give a yes. And if both are yes or both are no, then just give a no, like it's looking like this, okay? Okay, or you can have the white lights or have it blink here, either way. But the problem is that with single perceptron, which can only draw one line here, it's like a line, there's just no way to separate. You can either call this here yes or here, and it just doesn't work, isn't it? And even for the simple thing, the perceptron cannot do a job. What hope does it do to have like a birds flying and all this complicated thing? So that led to disappointment, along with some other Light Hill report and care. And there's negative news about this disappointment about this initial perceptron technology led to the first AI winter. Okay? Eventually, people found out the solution, and the answer is that, well, if you have multiple layers, then you can not only draw a line, but you can actually have a curved line, and you can curve it like this. Wow. And now you can separate it, isn't it? In terms of logic, if you care, you can basically have input A and input B and a logic table, and with the weights you have, and go up to the hidden node. So you have a multiple layer now, multiple nodes, and then we need here, and an output, you can actually implement an XOR. So the problem is that some problems can't be solved with just a single simple linear classifier, and you can use multiple nodes working together to solve many of these problems. So the AI boom picked up again. So here's the artificial neural network. So instead of just having one perceptron, so one neuron here like this, you can have multiple of them. So have multiple nodes, but also the stack of the nodes which receive multiple inputs. They are connected to our next layer, and you can connect here all and layer and all this. Okay, so then we call these the neurons, like this neurons like Hodgkin-Huxley, and the neurons, the axon, and the next stage dendrite meet here. This is the connection. Biology, we call it synapse. Okay? All right, and where does the learning actually happen? Well, people tried many things. You could have it, let's say, changing the activation function here, or you can have some nodes disappear. Many ideas were tried, but eventually people think that what happens in nature and biologically confirmed is that the strength of this connection between one node and another node, which we call synapse, the strength or the efficiency of transmitting the electric signal rapidly increased for the nodes that are important in learning. So what computer scientists try to implement here is that change the link weights, increase it to a larger number, or increase the synaptic strength between the nodes. That's how the learning happens, and that's what we mean by learning a neural network. So this is sort of summarizing the natural brain can do sophisticated things and fairly resilient actually to damage, in the sense that if one of these node breaks or input is corrupted, still the rest of them will do cover and adapt itself to do a reasonable job, like the traditional computer, which if it breaks, the whole circuit breaks down and so forth. So trying to copy biological brains partly inspired the artificial neural network, like the perceptrons and the subsequent innovations. And the link weights are adjustable parameter where the learning is basically happening. So thank you for watching this video. And in the next, we'll go through an example.